Okay, so our goal in this lecture is to study what happens if a linear transformation, or rather a linear operator on a finite dimensional vector space, is diagonalizable, and what is the concept of an annihilating polynomial, and eventually we will be studying what the minimal polynomial of a linear operator is. Okay, so let's start. So I will obviously assume that the basic terminologies regarding this lecture is well known to the listeners. For example, what diagonalization basically is, what a linear operator is, what is meant by a basis of a vector space, what is meant by a finite dimensional vector space, and so on and so forth. Okay, so let's start. So let P be a diagonalizable be a diagonalizable operator operator on a finite dimensional vector space V. Okay, and say V is defined over the field F. Okay. Let B, which is given as alpha 1, alpha 2 till alpha n, be an ordered basis, of V, which consists of the eigenvectors of T relative to the eigenvalues say C1, C2, and so on till Cn. Okay, and obviously we are not concerned about whether these eigenvalues are distinct or whatever. So now obviously we know that in that case P of alpha I must be of the form Ci alpha I, right? So obviously from this representation it is pretty clear that the matrix representation of this linear operator T with respect to the basis B is nothing but a diagonal matrix. So it's of the form C1, C2, and so on till Cn, right? Okay. But obviously, since we do not know that whether um, you know whether these eigenvalues C1 till Cn are distinct, or are, there might be a repetition of these eigenvalues. That is, you know uh, there can be, three repetitions of C1. That is basically what I mean to say, is that we know that the eigenvalues are roots of the characteristic polynomial, right? So the characteristic polynomial obviously of this form. So it's determinant of, rather I should use the term determinant of this minus xi, right? So this is the characteristic polynomial of this linear operator T. And suppose this is of the form x minus c1 to the power d1, x minus, or rather I should slightly change the notation of this eigenvalues. So it's like, say, c1 d1 x minus c2 d2, and so on till x minus ck dk, where each cj is some ci. Okay, so ci is obviously represent this listing, and cj's are these values. So what I actually mean to say is that this gives us a representation of which actually includes the algebraic multiplicity, or the number of times each eigenvalue exists as the root of the characteristic polynomial. Okay. For example, if the matrix is of the form, let's say, suppose the characteristic polynomial of A is of the form, let's say, x minus 1 squared, x minus 2 cubed, and x minus 3. So the eigenvalues, if listed, in a way, on a simple note, for example, like this, then they are just 1, 2, and 3, right? So we are not actually including the repetitions of each of these eigenvalues. So these Cj listing, it's actually of the form. So we have two ones, right? So we have two ones, three twos, and one three. Yeah, right. So each Cj, that is each Cj, is some element from these listings, right? So I guess now it's pretty easy to notice, right? So the concern is that. So let me just come up with an example, and then it will be better to understand. Okay. So let us just start with an example to establish what I am trying to say. So let the matrix representation of T with respect to the basis B is say of the form 1 0 0, or rather let me just write the values only. I don't need to write the zeros. So you have say 1 1, 2 2, and 3 3. Okay, all these rest are zeros. Okay. So if I let's release down the rows, so this is I equals to 1, I equals to 2, I equals to 3, I equals to 4, I equals to 5, and I equals to 6. Right? Clear? So you can obviously notice that if I consider these Cj's, or rather I should say C1, C2, C3 to be the distinct eigenvectors, then you have them as C1 equal to 1, C2 equal to 2, and C3 equal to 3, right? So one thing I just, there was a slight misuse of the, I mean a slight exchange in the notation. This was the representation of Ci's, right? And this was the representation of Cj's. So Cj's actually are, are basically the collection of the distinct eigenvalues. So 1, 2, and 3 are the distinct eigenvalues, right? So C upper index J's are the distinct eigenvalues, while C lower index I, they represent actually the every eigenvalue respected to their multiplicities. Okay? So this is C1, C index 1, C index 2, upper index 2, and C upper index 3. Clear? So C1, C upper index 1, C upper index 2, and C upper index 3 are the respected eigenvalues 1, 2, and 3. Okay. And if I consider the listing in the lower indexes, then we have C1 is 1, C2 is 2, C3 is C2 is 1, again C3 is 2, C4 is 2, C5 is 3, and C6 is 3 as well, right? And also obviously we can notice that what are the algebraic multiplicities of each of these eigenvalues. So we can obviously notice that the algebraic multiplicity of C1 is 2, similarly that of C2 is 2 again, and that of C3 is 2 again. So obviously C1, the eigenvalue C1 is present in this listing twice, and which is obvious. 2 is present twice and 3 is present twice as well. Clear? So suppose so obviously with respect to the form in which we write the characteristic polynomial, we can say that the degree of C upper index 1 with respect to the characteristic polynomial is denoted at d1, so it's 2, then d2 is 2 as well, and d3 is 2 as well. Observe that d1 plus d2 plus d3 is 6, which is equals to the dimension of the matrix A, right? So I guess it's pretty clear to notice. Okay, yeah. And further you can also notice that C upper index 1 is equals to C lower index 1 from I equals to 1 to I equals to 2, right? Right. Or rather I should write, yeah, it's pretty easy to notice, right? Right. So C upper index 1, in the sense you have this value 1, right? So C upper index 1 is equals to C lower index 1. So it's this value, right? So I should write here I. This will be better to understand, right? Right? Yeah. Then C upper index 2 is equals to, further observe that this value is nothing but d1, right? This value is d1. Then you have C upper index 2 equals to Ci from I equals to, I guess it's from 3 to I equals to 4, and this is nothing but d1 plus 1, and this is nothing but d1 plus d2. Similarly, we have c3 equals to ci from I equals to 5 to I equals to 6, and this is basically d2 plus 1, and this is d2 plus d3, right? Right. So what does this actually help us to do? So if I write this set of statements in the form of a theoretical statement, it seems like this. So we can write it like this. So let T has k distinct eigenvalues. So it's C1, C2, C3, and so on till Ck. Let Cj equals to Ci when, so we just relayed whatever we have here, right? So when I equals to 1 plus summation over ds, and so we have these, so where does this ds run? Okay, so from this to, we have summation over ds s equals to 1 j, right? So it comes from s equals to 1 to j minus 1, right? S equals to 1 to j minus 1, right? Yeah. And summation over j equals to 1 to k, s is equals to n. Clear? Okay. So you can obviously relate this to here. So here you had, this is equals to d1. So s equals to 1 to 1. You have d1. Here you had nothing. So I started with 1. Right? Clear? Then here you had 1 plus d1 because you had j equal to 1. So s equal to 1 to j equal to 1. You had d1 plus 1. And here you had d1 plus d1 plus d2. So it started from, so from this to it went to this. So in this case j equals to 2, right? So s equals to 1 to 2. So it becomes d1 plus d2, and so on and so forth. So the actual thing which we want to say is that provided this happens, because this is not provided this happens, because this actually happens, right? So T obviously catches up with this form. So you can write T in this form. So you have C1, C1, right? So this is a D1 cross D1 matrix. Then you have C2. So this is a D2 cross D2 matrix, and so on till you have, some Cn. Yeah. So this is a block diagonal form, right? This is a block diagonal form. So whenever you have repetitions, you can form in this way. I have again used a slightly abuse of notation here because I have represented the matrix as 2 cross 2 form, but here written the dimension as d1 cross d1. So it's better to write it in the form. So if I do not use this notation specifically, I can obviously represent them in the form. So if C1 appears D1 times, right? D1 is the multiplicity of the uh, of the distinct eigenvalue C1. So we can write it as C1 times I, which is of the form of the dimension D1 cross D1, right? Then you have C2. Here you have D2 cross D2, and so on till you have CK. Here I is of the form DK cross DK, right? This is pretty easy to understand, right? And pretty obviously you can notice from here, which I had actually started the discussion with, that the characteristic polynomial of T is obviously of the form x minus C1 to the power T1, and so on till x minus Ck to the power Dk, which is pretty obvious from the fact we started this discussion, right? But the main thing to notice here is that what is the null space of, if I represent this matrix, so this should be of this form, right? Yeah. So if I represent the matrix as D, so what is the null space of D minus C1I, let's say, right? So the null, so what happens if you subtract C1 from this? So these rows become 0, right? these rows become 0, but the rest of the rows has no influence. But the rest of the rows have no influence, right? So the null space actually consists of d1 rows. Right? It consists of d1 rows. Right? So this should be, so from here we say d1 rows are 0. Right? So the dimension of this null space is technically d1. Right? It's technically d1. So on a general basis, we can say that the dimension of the null space of d minus cji is nothing but small dj. Right? So that is what we actually wanted to say. Now, obviously, we know that the null space of d minus cji is basically the eigenspace of wj, right? So the dimension of wj is small dj, and since we had previously, saw the fact that summation over dj, j equal to 1 to k, it comes out to be n is the dimension of v, then obviously we can say that the summation of the dimension of each of these eigenspaces equals the dimension of V. And that's the fact about a diagonalizable linear operator. Diagonalizable linear operator. So the eigenspaces you get with respect to the distinct eigenvalues, the summation will give you the summation of the dimension will give you the whole vector space. Dimension of the whole vector space. Right? I should use the dimension. Yeah. Correct? Okay. So that is the fact which we wanted to tell. And so the converse is also specifically true, but that's going to be a topic of some other lecture. That is, if V is diagonalizable, this happens, right? But if this happens, D is diagonalizable too. We will be concerned about that fact in some later lecture. That is, if you have W1, W2 till Wk be the eigenspaces of the distinct eigenvalues C1 till Ck, then if the dimension of each of them equal the dimension of V, then V is diagonalizable. V is diagonalizable. And a hint towards this is pretty easy to understand, because if this happens, that's a very independent proposition. So that's why I said that to be a topic of some other lecture. But the typical thing is that if that happens, then the basis, if I consider basis from each W1 Wi, so suppose I consider B1 to be the basis of W1, B2 to be the basis of W2, and Bk to be the basis of Wk, then B1, B2, Bk arranged column wise as vectors, they form the basis of the vector space V. Okay, and if so happens, then also it is pretty easy to understand the fact that this matrix, suppose this is the matrix V. Okay, and then what happens is basically, if you have say A to be the representation of T with respect to this basis BV, then AP is nothing but, you have A beta 1, A beta 2, and so on till A beta k. But obviously beta 1, beta 2, and beta k, they represent the eigenvalues. So you have so they become C1 beta 1, C2 beta 2, and so on till Ck beta k. And that's nothing but P times I. Right? Sorry, P times D. P times D. But D is the, this form, C1, C2, Cn. Obviously in the block diagonal form, because we do not know whether, because when we break them down, right, you will get obviously the multiple eigenvalues as well listed here. We are not concerned about them when we are having this multiplication, right? So you will have this form where C1 appears, some D1 times, C2 appears some D2 times. But indeed it's a diagonal matrix. So you get the form AP is equals to PD, which implies A can be written as P, D, P inverse, or rather the general notation is D can be written as P inverse AP, right? So that's that's a topic of some other lecture. We will be obviously concerned about that in some later video. Okay. So let's come to the concept of an annihilating polynomial. I think I have a lecture where I slightly explain the concept of eigenvectors, eigenvalues, what diagonalization typically means, how it actually happens geometrically. I obviously couldn't use the visual aspect of the diagonalization on a geometrical basis, but I try to explain as much as I can. So I'll obviously use that, and I will give the reference to that video in the I button. Okay, so I have the annihilating polynomial. So the very basic definition is like this. Let T be a linear operator on a vector space df. Let fx be a polynomial. Let fx be a polynomial over f. Then ft is also a linear operator on V if ft is 0, then such polynomials are called the annihilating polynomials. The annihilating polynomials of the linear operator T. Okay, so to be very precise, if you have a polynomial over the field f which maps T to 0, then obviously that polynomial f is said to be an annihilating polynomial. The most fundamental example you have is the characteristic polynomial, because we you know that's a claim which will you prove later, because that's a very complicated discussion. We'll prove it in some later lecture. But the characteristic polynomial annihilates its linear operator. Clear? Clear? Okay. Got it? Okay. Notice one thing, that an observation. Okay. The observation is of the form that suppose you have a linear operator T. Okay. You have a linear operator T and you consider f to be an arbitrary polynomial over the field f. Okay. So let T be a linear operator and let f be a polynomial over f. Okay. So let T be a linear operator over V and f is a polynomial over f. F is obviously the underlying field. Then what is ft? So suppose fx is of this form. So it's a0 plus a1x and so on till some anx to the power n, let's say. Then what is f of t? So f of t is typically, or f of t of alpha, let's to be precise, because alpha is, alpha we require the alpha because t is a mapping indeed, right? So it's of the form a0 I of alpha plus a1 t alpha plus a2 t squared alpha and so on till an t to the power n, right? Now suppose so obviously if t is a linear operator, then ft is also a linear operator. So that implies ft is a linear operator, and that is what we have used in this definition, that ft is also a linear operator on V. Furthermore, you can also view the following fact, that if t has a has an eigenvalue, say c, whose corresponding eigenvector is alpha. Suppose c is an eigenvalue of t with eigenvector alpha, then ft of alpha, which is written in this form, so it's a0, so I of alpha is alpha, right? So plus you have here, so c1 t of alpha, so a1 t alpha, so this becomes a1 c alpha, right? Because T of alpha is C of alpha because C is an eigenvalue of T whose eigenvector is alpha. Plus, so you have A2 T squared alpha is nothing but C squared alpha. C squared into alpha. No, you can obviously notice this that T R alpha. So this is basically T of T of T and it appears R times of alpha. So if I consider suppose T2 alpha, you can obviously inductively observe this. So there's no need to complicate it. We can just consider it using T2 alpha. So what is T2 of alpha? Where C is an eigenvalue and alpha is the corresponding eigenvector. So it's T of T alpha, but T alpha is C alpha. So it's T of C alpha. C is a constant, right? So C comes out. So it becomes C times T alpha. T alpha is again C alpha. So it becomes C squared, right? So it's C squared alpha plus you have here A3 C cubed alpha and so on till you have here an C to the power n alpha. So you can obviously consider alpha outside. So it becomes A0 plus A1C and so on till an C to the power n times alpha. And this is nothing but f of c, right? F of c. That's a quick observation we have, right? About polynomials. Okay. So let's come back to our lecture. Okay. Yeah. So suppose f is an annihilating polynomial. Suppose ft is 0, where t is a linear operator on the vector space V over f, and f is a polynomial from the underlying field. Clear? Now, if gx belongs to fx such that fx, this f is a factor of g, so it's fx times some rx, then that implies g of t is nothing but f of t times r of t, but f of t is 0, so it becomes 0 as well, right? So obviously any multiple of an annihilating polynomial is again an annihilating polynomial, right? Clear? Okay. So observation number 2. So this observation requires the concept of an ideal. I won't be discussing that here. So observation is that the set of all polynomials which annihilate t will form an ideal of fx. Okay, let me just give a brief description of what we are trying to say. So what is an ideal? So ideal of a ring fx, where f is the field. So obviously it's a commutative ring with identity, right? So we consider a commutative ring just simply. Okay. So let I be a subset of a commutative ring with identity, say A. Clear? We are considering a commutative ring to to abolish or avoid the concept of a left ideal and a right ideal. So I say to be an ideal if I is an ideal if for all A B in I, A minus B is again in I. So this is number 1. Number 2 is for all A in I and for all elements R from capital A RA is inside I, right? RA is inside I. Okay. Now we can obviously verify this from our definition, because if you have say F and G are from the collection, say we represent the collection as say like this. So F is the set of all annihilating polynomials of T. Okay. And obviously this set is a subset of fx, right? Because it contains polynomials over the field f. So it's obviously a subset of fx. And that's also quite pretty easily noticeable that they are not equal, right? Every polynomial, there are infinite number of polynomials over the field f. So every polynomial will obviously not annihilate the given linear operator, right? That's pretty easy to notice. So if f and g are annihilating polynomials of T, then obviously notice that fx minus gx, which is nothing but ft minus gt is nothing but f minus g of t. So it's zero because this is zero and this is zero. So that implies f minus g is in t. And if you consider g to be an element from fx, then gt times ft, but f is an element from at, that's equal to zero because ft is zero. So that means gf is in, right? So this is clarified. Got it? Clear? So the basic thing is that if this forms an ideal of fx, then there must exist a monic generator, right? A monic generator of this ideal. That's the polynomial concept of a polynomial algebra. Okay. To be precise of that fact, we first consider the following question. You might say that if T from V to V is a linear operator, where V is a vector space over F, the vector space, then is there any finite degree polynomial, small p, which annihilates T, right? Because if we have no concept of a finite degree, then we cannot be precise of the fact that there's a monic generator. We need to have something in our hand, and to have some polynomial in our hand requires that polynomial to be a finite degree, right? And this question has an obvious answer when V is a finite dimensional vector space, right? So if V is a finite dimensional vector space, then the characteristic polynomial of the linear operator T is of finite degree, and it annihilates T, and it annihilates T. Okay, this actually is called the Cayley-Hamilton theorem. Cayley-Hamilton theorem. We will prove this later. A very important theorem in matrix theory. Clear? Okay. So indeed, if V is a finite dimensional vector space, then we have a finite degree polynomial which annihilates the linear operator defined on that vector space. Clear? We can also view this by constructing one such polynomial, which is also pretty easy to do. Observe that. So notice that if T is a linear operator over V, then any integral power of T is also a linear operator on V, right? So LVW is the set of all linear transformations from V to W, and this set forms a vector space over the composition operation. So LVV is also a vector space over composition operation, and it is basically the set of all linear operators on V by the precise definition, right? And previously we had proved, I think we have that lecture in some video of mine on my channel. I don't exactly remember, but the dimension of LVW provided that V and W are finite dimensional. So if V and W are finite dimensional with dimensions say n and m respectively, then LVW has the dimension nm. Clear? So obviously the dimension of LVV is n squared provided the dimension of V is n. Furthermore, if dimension of V equals n, then the dimension of LVV is n squared. Okay. What we do is that we consider the polynomials of this form. Let S be this set. T0 is basically identity. Okay. So where T0 represents identity operation, identity linear operator. So let us consider this T0, T to the power 1, T squared and so on till T to the power n squared, where TR is nothing but the composition of TR times. It's T of T of T and so on, of T of some alpha. So this happens R times. Clear? So what are the number of elements in S? The number of elements in S is S square plus 1, n square plus 1. The dimension of LVV is n squared, but the number of elements in S is n squared plus 1. Therefore, S is a linearly dependent set, right? Because the maximal maximum number of elements in a linearly independent set can be n squared, because dimension is n squared itself. So S must be a linearly dependent set because it has elements more than the provided dimension. Right? So that means there exist scalars a0, a1 till say an squared, not all 0, such that a0 t0 plus a1 t1 so on till an squared tn squared, this is equal to 0, right? Obviously of some alpha, we are not mentioning that, that's quite trivial to notice, right? So that means fx, which can be written as a0 plus a1x and so on till an x to the power n square x to the power x to the power n square, is a finite degree annihilating polynomial of t, right? Because ft is nothing but this, right? Yeah. Therefore, if you have a finite dimensional vector space, then there obviously exist finite degree annihilating polynomials of the linear operator. Clear? Right? So this comes to the next immediate concept, which is the concept of a minimal polynomial. So we discuss that, introduce that in this form. Let T be a linear operator on a finite dimensional vector space V over the field F. Then there exists a polynomial fx such that ft is 0 and degree of f is finite. Now, the set of all polynomials which annihilates T forms an ideal and consists of finite degree polynomial, has a least degree. So we obviously, since it is a finite degree polynomial, so we can talk about the least degree concept, right? So it is a least degree monic generator, right? Monic generator denoted as px, and obviously which satisfies these conditions that p of t is 0, and number 2, if some qx is in fx such that qt is equal to 0, then P must divide Q. And this is quite evident from the fact, because if Q annihilates T, then Q must be an element of the set of all annihilating polynomials of T. If it is inside the set of all polynomials which annihilate T, then it must be a multiple of the polynomial P, because P generates that ideal, right? So this is quite evident from here. Got it? Okay. So having defined the concept of a minimum, okay, so this P is called the minimal polynomial. This least degree monic generator of the ideal of the annihilating polynomial ideal of T is called the minimal polynomial of T. Clear? Now, when we have studied the concept of characteristic equations, we had the fact in our hand that similar matrices have same characteristic polynomial. So we have a related lemma that similar matrices have same minimal polynomial. Similar matrices have same minimal polynomial. Okay. So how can we prove this fact? Okay, so let P be the minimal polynomial of say B, where B is some matrix representation of P. Now it is quite evident from the discussion of linear transformations over finite dimensional vector spaces and matrices that they are actually they correspond to each other, right? Linear transformations and matrices are actually the same concepts over finite dimensional vector spaces, because they correspond to each other. So the same definition and the same concepts, they are related to the matrices as well. So obviously the minimal polynomial of a matrix is basically the least degree monic generator of the set of all polynomials which annihilate the very matrix. And annihilating a matrix is also quite trivial to notice, because it's the same definition. It has the same definition. So let P be the minimal polynomial of a matrix B, where B is some matrix representation of T. We won't use this term anymore. And let A be similar to B. Similarity. Okay, A is similar to B. Now P of B is 0, right? So that implies, okay, let P be of the form AI x to the power I equals to say 0 to k. Okay, then P of B is of the form summation over I is equals to 0 to k AI b to the power I, where b to the power 0 is the identity matrix, right? Okay. Then since A and B are similar, so A is nothing but P inverse BP, right? Since A is similar to B, there exists invertible matrices P such that A can be written as P inverse BP. And obviously, I think this is pretty trivial to notice that A to the power some J is P inverse B to the power J P, right? Because what is A squared? So A squared is P inverse B P times P inverse B P. So we can associate P and P inverse, that gives you identity, so it becomes P inverse B squared P, right? Now inductively you can obviously prove this fact, right? Therefore, P of A is nothing but summation over I equals to 0 to k AI P inverse B P, sorry, P, yeah. So we have the concept of A, right? So we can represent this in this form. So wait a minute. Yeah, we should have written it like this. So A to the power I, but A to the power I is nothing but P inverse B P whole to the power I. And this is nothing but AI P inverse b to the power I, and this can be obviously written as P inverse times the polynomial AI b to the power IP. So this is 0, right? So the whole thing is 0, right? Now this is a symmetric definition. Now this is a symmetric definition. So what do we actually claim from here? So we claim from here that P of A is 0, right? And so that means that P divides the every annihilating polynomial of A. And since it is a symmetric definition, that we can reverse the fact, that is, since A is related to B implies B is related to A. So eventually coming up with this definition will provide the concept that A has B as its minimal polynomial. Okay. So that is for all for this lecture, guys. In the next lecture, we will be discussing the other concepts related to annihilating polynomials and minimal polynomials. Okay. So meet you guys in the next lecture.